All right, 13.3, we're going to look at factors that affect solubility. Okay, and here are the 4 basic ones that affect how well things dissolve. Because solubility, remember, is the tendency of something to dissolve. Okay, we have the nature of the solute and the nature of the solvent. So again, you got to be careful with that interaction between the solute and the solvent, and whether your solute is a stronger bond or your solvent that's trying to rip it apart is a stronger bond. We're also going to have temperature, and you're also going to have pressure when we look at gases. Okay, so the main one again is that one that I just said. Okay, it would be the strength of your solute-solvent interactions, and the strength of this interaction is a big deal. Otherwise, your substances would always just mix because entropy increases when things mix. So you've always got to look at exactly which one is stronger, the solute or the solvent. Are they equally strong, which means they're probably going to dissolve, or is one way too strong for the other? Okay, so that's the first big one there, solute-solvent interaction. And we're going to look a little more closely now at the different types of forces here. Okay, first one is a London dispersion force. So the only force, anytime we have this as the predominant force, is going to be in a nonpolar covalent bond. Okay. Now remember that London dispersion force increases as your size increases. Okay. So as your attraction increases between a solute, which we're going to look at a gas here, and a solvent, a water, your solubility goes way up. And so we look at this chart here you have in your notes, okay, and notice how my numbers, okay, get bigger. All right. Now that means my attraction should be getting bigger. All right. Now krypton, we look and we see, is heavier than argon, heavier than oxygen, heavier than nitrogen, which would make sense because my London dispersion force increases as my mass gets bigger. So my mass gets bigger, the force of the attraction between two London dispersions gets stronger, okay, and my solubility then starts to go up. So it makes it easier then for the gas to dissolve in water, okay, which kind of makes sense because you're kind of getting water, which is polar, and a London dispersion force, which is nonpolar. So your water is trying to rip apart something that is nonpolar. As they get closer kind of in strengths, your solubility actually goes up. Okay, we have a dipole. Dipole, which is your polar solute, dissolves in a polar solvent. And as your attraction increases, your solubility increases again. So as your dipole moment kind of goes up, it gets easier to dissolve. And when we're talking about things in water. Okay. And we're also dealing here with dipole, we're also dealing with hydrogen bonds as well. Pretty much when we talk about solubility, we're dealing with things dissolving in water. Okay, we have a couple of words here that we've got to make sure we know what they mean. We have miscible and we have immiscible. Miscible liquids are pairs of liquids that mix in any proportion, meaning they're always going to mix, and it's always two liquids when we use these terms. So salt and water we don't call miscible. Okay, immiscible are liquids that don't mix very well. Okay, oil and water, salad dressing, things like that are going to kind of settle out, and you're going to have a heterogeneous mixture. We're going to have the two liquids that don't mix. Okay, these are because they do not have a strong solute-solvent interaction. Your solute and your solvent don't want to mix. One is way stronger than the other and would much rather bond with itself than try and rip apart something so weak. Or the other way around, the weak ones can't pull apart the really strong ones. Okay, a little bit of both there. So you've got miscible and immiscible. Okay, another part of these solute-solvent interactions is going to be the solubility of alcohols in water. So if we've got hydrogen bonds, okay, and if we have an alcohol, alcohols have OHs on the end, and I have one circled here, okay, and you had something similar on your take-home for chapter 11, okay, they form hydrogen bonds on the end with water and other alcohols because they have OHs on the end. So this OH here is connected, and it's kind of a dotted. So this OH here is kind of connected, and it's like a dotted line here, okay, to another water, and that's the blue hydrogen bond there. I have an O on one and an H on the other. Okay. Now your solute, solvent, solvent, and solute, solvent are not very different. Okay, plus an increase in entropy, so they are very, very miscible. And alcohol will dissolve very, very easily in water because they are very like attractions. Plus your randomness is increasing. Okay, so when we look at these, your solubility does at some point in time kind of slow down. Okay, it has to do with your number of carbon atoms. So as your carbon chain increases, it begins to act more like what we call a hydrocarbon, which is just C and H, which is nonpolar. Okay, so we have these ones on the end, and mine's really blurry, but yours should not be. These bottom three, which are butanol, pentanol, and hexanol, where we have more carbons, see how long that chain is, we start to actually get numbers for how well they dissolve in water. Whereas they are completely soluble in something that is nonpolar, okay, which is going to be hexane. But look how these first ones are very, very soluble in water, because these are way more polar because the chain is a lot shorter, okay? The more massive ones are less polar and dissolve more easily in a nonpolar because they're acting more nonpolar, whereas the shorter ones, the water is a way more integral part, or the OH is a way more integral part, so it acts way more polar, okay? So that's kind of the hydrogen bond end to it, all right? All right, we have a generalization here, which is at the top of the next page, okay, which is like dissolves in like. Substances with similar intermolecular attractive forces tend to be soluble in one another. The more polar, the better it dissolves in a polar. The less polar, the better it dissolves in a less polar or a nonpolar. Okay, so we're going to predict whether each of the following is more likely to dissolve in a nonpolar solvent or in water. So we have our nonpolar solvent, which is CCl4, or we have water, which is our polar one. Okay, so we've got C7H16. That one is very nonpolar. Okay, there's carbon and hydrogen don't have that big of a difference. Okay, I2 is very nonpolar, because there's no difference there in electronegativities. HCl is very polar. Chlorine really wants electrons, hydrogen really doesn't. Na2SO4 is actually so polar that we are looking at an ionic one. Okay, so think about which ones are going to dissolve in what. So I have two nonpolars, which should both dissolve in CCl4, which is my nonpolar. I have one that's polar and one that's ionic, but they still both have positive and negative sides. Like I kind of said, their ionic is just actually so polar that it's its own, it's a total positive and a total negative versus partials. So these are both going to dissolve very well in water, which is very polar. Okay, so those are my solute-solvent interactions. Look at the type of bond, okay, and how well one will dissolve the other based on how strong they are. The next thing is a pressure effect, okay. When we look at solubility for solids and liquids with pressure, we're not greatly affecting pressure because they don't compress. So if I have a solid or liquid, it's not going to dissolve better or less if I have more or less pressure because they really don't compress. They're already as close as you can get them together, okay. But if we look at a gas, okay, your solubility will increase as your pressure increases. The higher the pressure, your molecules are now closer to your surface and are more likely to strike your surface and enter the solution. If it's a lower pressure, your particles are further from your surface and don't dissolve. Because remember, solubility is all about dissolving in my solvent. So if you have a higher pressure, okay, I have my solvent there, we start pushing down on it, all right, creating a smaller volume. These gas particles are now going to be forced to be closer to my surface, so now more of these are going to hit the surface, be recaptured, and dissolve. That is solubility, being able to dissolve, okay? We do have a law with this one and a little bit of math, okay? Henry's law, it says the solubility of gas is proportional to the partial pressure of the gas above the solution, okay? If your solubility wants to go up, you got to have a higher pressure. Get more gas particles there, make the volume smaller, do something to make your partial pressure go up. It's just how pop is bottled. Pop is bottled under a pressure greater than 1. When you open the bottle, the pressure goes down, and as the pressure decreases, the solubility decreases, and the CO2 comes out of the solution. That's where you get all that fizz from pop. But pop that's flat has lost all its CO2 because the pressure is now the same as it is around it, with 1. So they make those pop bottles a higher pressure to force the carbon dioxide into the pop. Then when you open it up, all the foam or CO2 leaves, and that's what makes it fizzy. So we have here our equation. Okay, we have the solubility of a gas, which is S with a little g, There's a solubility gas. We have K, which is a constant, and you're going to have all kinds of K's throughout the year here. But this is the particular constant for that particular gas. Okay, and then we have the pressure of the gas. So let's look at an example here. It says calculate the concentration of CO2 in a soft drink that was bottled with a partial pressure of CO2 of 4 over the liquid at 25 degrees. The Henry's law constant for CO2 and water at this temperature, and they give you the constant. They'll have to give you the constant. It's not always the same. Okay, so I want to know the concentration, which in essence we're looking at the solubility. How much dissolves, okay, and how many liters. Okay, so I've got my solubility equal to my constant, which is 3.1 times 10 to the negative second moles per liter times atmosphere. Okay, so then if I have times my partial pressure of 4 atmospheres, that's how we get moles per liter. Because the atmosphere here is on top, we're going to multiply it by an atmosphere on the bottom, so my atmospheres are going to cancel, which leaves me with moles per liter, which is molarity. We just multiply the two numbers and we should get 0.12 molar. And that is the pressure effect on solubility. Now let's look at the last one, which is temperature. Okay, solubility of solid solutes. Most increase in solubility as your temperature goes up because your particles are moving more quickly, so more particles combine and more dissolve. There are a few, though, that decrease as temperature decreases. Notice how most of these lines go up. As my temperature goes up, okay, to the right, we're increasing temperature. My solubility of most of these lines is increasing, which makes sense. We have one here that decreases. There are very few, but there are a couple. Okay, we got particles moving more quickly. More is going to dissolve because I have more temperature there. All right, that's for a solid. Now, if you look at a gas, all right, if we look at a gas, the solubility decreases as the temperature increases because not as much of the gas dissolves. If you have more temperature, you have more energy. If we have more energy, you're going to be more likely to have a gas. So more space and particles have more energy. They move quicker, so they escape to the gas phase easier. So looking at gases, it goes the other direction. Your solubility here goes down as your temperature goes up. Okay, and usually for a solution with solids, we look at the solubility in grams of the solid per grams of water. Here we're looking at kind of molarity wise. All right. Think about how pop gets flat as it gets warm. A glass of cold water will have bubbles on the side as it warms. Okay, your gas is starting to leave as the temperature goes up.